Welcome back, guys. Today we're going to talk about the difference between mass and weight. Mass is going to be the measure of how hard it is to accelerate something. So inertia is the tendency of something to stay at rest. In the SI system, our base unit for this is kilograms. Although very often outside of physics, these two are equated to each other, mass and weight are not the same. So mass is going to be the property of the object. This isn't going to change no matter where you go. Weight is going to be the force that gravity exerts on the object. And this would change even slightly if you go to the top of a building, the top of a mountain, and definitely if you go to a different planet. So if we're on the moon, we'd weigh a sixth as much. If we go to Jupiter, we'd weigh 2 times 8 as much. The mass, though, the amount of things that made you up would all be the same. And it would be just as hard to accelerate you on the moon as it is on Earth. So inertia is this tendency of an object not to accelerate. So something that is hard to move or something that's hard to stop moving has a lot of inertia. And this mass is a scalar. The unit of force is the combination of other bases. If you remember what our bases are, we have kilograms, meters, and seconds. So it turns out that force is going to be a kilogram times the meters per second squared. So looking at what these are, since kilograms are a measure of mass and meters per second squared are the units of acceleration, we could see that m times a, mass times acceleration, ends up being force. We have these other ones that we don't use. We've widely adopted the SI system, but you might come across dynes or ergs, and these are with the centimeter, gram, second systems. So weight is going to be equal to the mass times the acceleration due to gravity, and this is going to vary based on a number of different conditions, mainly being what planet you're on, but also where you're located on said planet and what the altitude is. So here's a picture of an astronaut, not the scale, and he's standing on the Earth, and his mass is 120 kilograms, so his weight ends up being 1,200 newtons. Same astronaut now goes to the moon, again, not the scale. His mass is still 120, but now his weight is only 200. So it would take a sixth of the force to lift him on the moon, but it would be equally hard to accelerate him because his inertia didn't change. His mass didn't change. Another example, somebody on the Earth that weighs 140 pounds, taken to the moon, would weigh only 23 pounds. Same person taken to Jupiter would now weigh 355 pounds, or if you take them to the surface of the sun, they'd weigh 3,914 pounds. Although if you took someone to the surface of the sun, the increase in weight would be the least of their problems. All right, this section is going to completely deal with Newton's first law.